The particle zoo. Physics is a simple but subtle attribute to P. R. Lenfest. Particle physics in the 1950s and the early 1960s was definitely experiment driven. There were these new accelerators which were being built mostly by the US government, and some were being built in Europe, where people were producing new particles. You would see trucks in the bubble chamber pictures, or more sophisticated detectors. People were beginning to discover that there was more to the world than just protons, neutrons, and electrons, even more than adding in the muon and the pion. There were whole families of the new particles which were more massive and which require a great deal of energy to produce. They were radioactive and would decay quite rapidly. People were a little bit overwhelmed. What were these things? So they started just to categorize. It was in a certain sense analogous to what was going on when the Tycho Brahe in the 1500s was looking at the motion of the planets, just trying to collect the data, hoping that somebody like the Johannes Kepler might come along later and start to explain what was going on. In today's lecture, we are going to talk about the zoo of particles and the first steps towards organizing and understanding what was going on. We are going to talk about a puzzle that was solved, which helped us to organize these particles. That puzzle was kind of another who ordered that sort of situation, something that had not been expected. There wasn't any obvious reason for it, but it was a principle that allowed us to begin to make some sense of this really overwhelmingly complicated zoo of the particles. These heavy things that decayed and turned into the protons and neutrons and pions and electrons, the kind of the ordinary stuff that the regular world is made of. Around the 1950s, some rather unusual trucks started showing up in the bubble chamber pictures. They were called strange particles because at first there were some just curious aspects of these trucks that didn't really make sense. There were a couple of curious aspects. First of all, these particle trucks, and here is a bubble chamber picture where you can see nothing, and the V which just appears. V just appears. This was called a V particle at first, and how can you explain that? Some particle just appearing out of nowhere? Well, that's not so hard to explain. Most likely, there was some electrically neutral particle that had been produced earlier and was traveling through your bubble chamber. But since was electrically neutral, maybe it wasn't ionizing. Then it fell apart. It radioactively decayed. What's puzzling is why did it take so long? When you produce a particle in the bubble chamber, it's usually a strong interaction of the nature. It's protons whacking into other protons and neutrons and pions. There are all very strong forces of nature, highly probable events. And what you expect if you produce a neutral particle is that it should decay very quickly. So what's unusual is that that V is so widely separated from anything else in the picture. Apparently you have some long-lived particle, and that seems a little strange. If you produce a particle strongly, it should decay strongly because it's a strongly interacting particle. That was the idea, that was a world view that people had. That was a puzzle that we were facing. There was an additional strange element of this story, which was that when you see one V truck, you almost always see another V somewhere else in your bubble chamber image. Sometimes it's off to the side of the image, but usually they come in pairs. This was called associated production. So if you are making one strange event, you usually make two of them, and that also was a puzzle that really just couldn't be explained in any obvious way. Well, I guess this is because of the keeping the law of conservation. Once you make something radical, you have to make another one in order to make zero, make it make complements, make not radical. So adding both of them make a neutral zero, meaning no violation for conservation law, right? No, I will see it. The solution to this puzzle, at least the first solution, came from a young theorist named Murray Gell-Mann. Murray Gell-Mann turned out to be one of the big players in this story. As events progressed, he was the one who really helped us make sense of this zoo of particles, and here was his proposition. He said, suppose that the fundamental particles have another characteristic, another property, besides all the one we've considered. What have we considered so far? We have a mass, we have an electric charge, we have a spin. How much angular momentum do they have? There are properties that we can tabulate. We can write down the numbers. Every particle has a certain amount of all of those things. We call those things quantum numbers because they are numbers that describe and identify the particle. Murray Gell-Mann proposed that there was one more quantum number associated with every particle that we had never thought of before, and he gave it the lovely name of strangeness. Because there were strange particles, so he said, you can have a certain amount of the strangeness as a particle. You could have a strangeness 0, and that means you are normal. That's like a proton, or a neutron, or a pion, or any of the particles that have been known up to this point. Right. They have 0 strangeness, but then he proposed that there was a new particle being produced. Because we've gone up to higher energies and we could make new exotic particles that was a strangeness 1. It's a quantum number, so it's going to come in the chunk. This was a Murray Gell-Mann's hypothesis, and then you had to see whether it matched the data or not. Now, how did they explain what was going on? Here is his proposal. When you have a stronger interaction, like the pions walking into the protons and something happens, there might be a transformation and you might produce a new object, but it's happening because of the strong force. His proposal says, the strong force preserves total strangeness. If you start with 0, you have to end with 0, okay? This conservation of the strangeness was a very easily acceptable idea at that time because we knew that the energy was conserved. The total energy coming in had to equal to the total energy going out. We knew that the total momentum was conserved. We know that total electric charge, another quantum number, was conserved. If you start off with no charge, you might produce a whole bunch of particles, some pluses, some minuses. But if you add them all up, it has to add up to what you started with. So, since all those things were conserved, maybe this new quantum number was also conserved by the strong force. So, if you're going to produce a strange particle, you are going to also have to produce at the same time a particle with a strangeness -1. That's why you are getting this associated production. You always have to make them in pairs. One will be strangeness plus 1 and one will be strangeness -1. They add up to 0, so you preserve to total strangeness. So that explains why the particles would have to come in pairs. Yes, I was right. I am right. Takayuki is right. Takayuki's prediction is accurate enough. But now, why do they live so long? Why were those V-tracks so isolated? Here's Murray Gell-Mann's answer. Even though the strong interaction conserves the strangeness, maybe the weak force of nature does not. Okay? Different forces can act differently. After all, the weak force was already known to be kind of the bizarre force. The weak force transforms a neutrino into a proton. Neutron. The weak force transforms a neutron into proton. That's a pretty radical change in the character of the particle, and that's only caused by the weak force of nature. So maybe the weak force can also change a strange particle into a non-strange particle. It can transform strangeness into known or known into strangeness. So that explains why it lasts so long. Whoa! So cool! Wow! Because once you've produced this strange particle, how is it going to decay? Okay, it wants to radioactively decay. But it decays strongly because if it's a strong decay and you have a strangeness one, you have to produce particles and at least one of them has to have strangeness. There are no other light particles that have a strangeness. Alright? So we are producing the first, very lightest particle with a strangeness here. There is nothing lighter than that carries a strangeness. So you are kind of the stuck. You are just traveling along. You want to decay strongly, but you can't because you can't get rid of your strangeness. So you have to wait until this improbable weak decay occurs. Wow! Improbable means you live a long time. Wow! Because it's hardly happen, right? Probability is low, meaning in order to make it happen, you have to just stay there till something happen to you. Now, you can get a quantitative with this idea. Because with a weak lifetime, you can actually do some estimates. You go all the way back to the theory of weak interactions written down by Enrico Fermi in the 1930s. Remember, that was a theory that involved neutrinos, and it predicted quantitatively what kind of weak decays can happen, and how strongly or how weakly they can occur. So, you can plug the number into that theory and surely enough, the lifetime that you are observing in this track is what we would call the weak lifetime. It corresponds very nicely, so this picture is coherent and it matches up with these so-called associated production of the strange particles. Now, you've produced various different strange particles. Apparently, one of them had a strangeness one, lived a long time, and then decayed. Another had a strangeness negative one, lived for a while, and decayed. So now, whenever you are tabulating particles, we have to tabulate not just change, mass, and spin, but also strangeness number. Wow! And make sure that this story is coherent, alright? You make up a story like this and it explains one or two pieces of data, but you are going to throw it away if that's all it does, alright? Especially if it's such a radical proposition, a whole new quantum number. You are only going to keep this idea if you can start to explain not just these events, but all events. So the search was on. Yeah. As the energy went up and the new particles were discovered, you would look to see, does this particle get created strongly and then decay weakly? Then it's a candidate for having a strangeness. Look for the interactions of those particles with other particles, and make sure that the strangeness is always preserved in all strong interactions, those that occur with high probability, and that it's violated only in those that occur weakly. It worked like a champ. It worked quantitatively. It began to assimilate a vast wealth of data. Yes, of course. Throughout the 1950s, there were many accelerators with lots and lots of particles being discovered. Hundreds by now had been discovered, and this idea of strangeness was really fitting in well. So it looked as though an organizing principle had been added to the story. conservation laws are very useful when you are trying to understand complex phenomena. Let's think about that for a second. If you have a principle such as a conservation of the electric charge, it's say that if a neutron strikes a proton, so you've got a total charge 0 plus 1 is 1. You might produce a whole bunch of particles. At first, you throw up your hands and say, well, anything can happen. This is quantum mechanics. If it can happen, it will. Alright? Particles happen, and the conservational law says, well, sorry, not anything can happen. You might produce some pions, but you have to make sure that the sum total charge is equal to 0, so you are limiting the possibilities of the nature by conservational law. This new conservational law is making some simplicity, some order out of the complexity of everything that could happen. Only a more limited number of events can occur. So that's nice, yes. As people began to look further, they discovered a few new particles, very massive, which had 2 units of the strangeness 2 or -2, and again, they fit in beautifully. If a strangeness 2 particle was created strongly, it would have to be involved in a process where you either had 2 strange particles coming in or 2 strange particles going out. Strangeness was conserved no matter what. So the principle continued to work. The weak force is getting a little bit weirder, alright? The weak force can now violate the conservational law, and we will see as we go on in the future lectures, the weak force has a history of being weird. It violates lots of conservation laws. Wah! It's just an unusual force of nature. It's a force associated with neutrinos, which are also kind of unusual particles, very exotic. Yes. Well, I think they just jumped in the the class of the world of the laws of class conservation. Although it looks like it violates the laws of conservational law, I think in total, in the bigger picture, it is it's still be 0, I guess. All these particles, the naming conventions are little confusing. I want once again to reiterate some of the various naming conventions. It's not that you necessarily have to memorize these words, but I will, from time to time, be talking about the type of particles we have, and it's nice to just have the sense of the scheme. So we've got a strongly interacting particles or not. The strongly interacting particles are going to be called the hadrons. Hadrons. And the weakly or not strongly interacting particles are going to be called leptons. Yes, leptons. The leptons include an electron or a muon or a neutrino. Those don't interact with the nuclei very strongly. Everything else, all the stuff you are seeing in the bubble chambers, and all the strongly interacting particles, protons, neutrons, and pions, etc., including all these strange particles, are all hadrons.